Wow, this is lesson 5, 5, 5, 10, 5, 11, 5, 12. Wrap up and just tying all the things together about the barometer, kinetic molecular theory, real gas. So, like, what in the world does this mean? What lesson is that? Okay, there is a worksheet. There are some worksheets to do. One of them is to complete the graph worksheets that I gave you a while back. I might repost them on this lesson. And then also to work all the kinetic molecular theory worksheets as well. There's no math involved in this. It's all conceptual. So what I'm just trying to do here is, like I told you, the last lesson, this might be more than one video, we'll see. But the last lessons are going to be just to a few days as you're reviewing, getting ready for the test. But these are some important things that you need to know. In fact, this is the concept. A lot of these are the concepts that all the gas laws are based on. And the scientists like Charles and Boyle and Gossack and Dalton, Avogadro especially, Graham, they didn't even know the reasons for what was going on. Why all the equations worked. They saw the observation. They didn't know the theory behind it. And so this will explain a lot of that theory behind it. Okay, so in the notes, I'm just kind of going through everything from 5.1. I'm just going to look through it for a minute. And I see 5.1, 5.2, we covered all that. 5.3, all the scientists, Charles Boyle, Gossack, Amadeo Avogadro. And then at the end, 5.5. Okay, here's an interesting thing I did not mention to you. 5.5 atmospheric pressure. Atmospheric pressure. Now, gases exert pressure. Why do gases exert pressure? Because the gas molecules collide with the object. Now, in a container, we say the gas, or a balloon, the gas molecules are constantly they're in constant motion, and we assume they're in constant straight line motion. What they call the ideal gas. They're not really, but they're constantly moving around, bumping into each other, bumping into the walls of the container, all around, like that. Well, as a net thing, anytime the molecule strikes the outside, that is causing pressure. The pressure with which they strike the side of the container is the same pressure they strike each other with. Okay, so everything moves around. Kind of a weird picture. Here's the bottom line, and I mentioned this before. Remember I said this. The pressure that is inside a balloon will always equal the pressure of the outside. So what atmospheric pressure is out here, and then we'll say your total pressure in the balloon is right there. Those two have to be equal. The pressure inside the container of a balloon, or if you're in a cylinder that has a movable piston. And I mentioned that before as well. Like, say if you have a container, like a syringe or something, and you close it off, okay, or maybe a bike pump and you hold the end of it so you can't push anything out of it. So what happens if you push this down? Since it can't escape, it'll compress it. It'll be a smaller volume under that higher pressure. You let go, it'll go right back up. So, well, anyway, here's the thing. If I heat this, the molecules inside will start moving faster, it will expand, but the pressure inside and outside are always equal. The atmospheric pressure here and the pressure total inside will always be equal if you have a movable piston, or if you have a balloon, or anything like that, an inflatable, whatever object. Now, if you have a rigid container, that won't be true, okay? The pressure, well, we'll talk about that in another case. But anyway, okay, so atmospheric pressure. I kind of got off the subject there with it. Oh, it's too bad. I'd show you if you saw the UCLA, we did this there. But anyway, one thing is to show you, oh boy, I have a mess over here. But I might be able to, oh my goodness, hold on. I spilled a bunch of liquid everywhere on my computer. I don't want to do that. This might work. Well, let's just see what happens. found something in here. I just had some things left over from the more recent UCLA that we did. Okay, I can show you this. This will work pretty good. Okay, you know that if you fill up water, like in a tube or in a glass, now you can submerge it in another fluid there in glass in water. And I got food coloring in there. Notice that it stays up. I may have shown you that on a video before as well. So what's keeping that up is the atmospheric pressure. The air is striking the surface of this container, and that's why the liquid is staying up inside there. Now, if I increase the pressure, more air, if I go to a higher pressure area, that level is going to go higher. If I go to a lower pressure area, it'll go down. Here's another way to say it. If I took air out of the room, out of a chamber, then this is going to fall down. Less air means less molecules are colliding, so there's less pressure going, less collisions means less pressure. It's going to go down. If I put more air, if I pressurize a chamber in an airplane, adding more air into higher pressure, it's going to make that go up as well. Okay? Now, all right. Why in the world does pressure increase, decrease like that? And who invented the barometer? Okay, that's what we're kind of looking at right here. So what I did was I used to draw a little cylinder like this, and I did this in a little diagram. Remember when you were like in, I don't know, maybe like 3 or 4 years old, and you ever went somewhere where they had like a ball cage, and they put like all these little plastic balls there, and you got down and you played in the nets, and you swam underneath it. My little boy, he loves doing that. My daughter, they play around in that. They're like, oh, yay, yay, yay. They're excited in there. Okay, little plastic pool of balls and stuff. They swim around in. Okay, let's just say that you had like this challenge or something. Your friend said, hey, how about we'll do this? We're going to pay you some money, or I don't know if they will do this, but you're going to go into a ball cage, but we're going to fill it up with some heavy objects, not balls. Like, let's just say like, I don't know. How about we're gonna fill it up with heavier balls, and you have to go and be submerged within it. So that means you got to be somewhere inside there. So I'll just say, like, I'll draw a little picture of a little friend. So here's a little girl. We'll put her down in there. There she is in the ball cage. Now you have to be surrounded on all sides by the balls. Would you rather be at the top, or would you rather be at the bottom? Think about that. Okay. Where would you rather be? And let's make it better. Let's just say that there's bowling balls in there. And you say you got to stay in there for at least 2 minutes. I mean, it'd be like almost like hard to breathe, wouldn't it, if you were down here in the bottom? So you'd rather be as close as you can to the top, like she is. And then when you're done, I mean, they'll do it slowly. They're not going to hurt you. They're going to put it around you, and then they're going to put some above you. So you'll be like, that would not be too comfortable. Now think about that for a minute. Why would it not be comfortable? Because you're getting pressure all around you. Think about that. Every direction. Because of gravity, actually. Gravity is pulling the molecules down. This is exactly what happens with the air. Gravity is pulling the molecules down. For all of them, not just the ones on the top. But see, as they pull them down, they're going to be pushing closer together to each other. And so, as a result, you're going to get pressure on you in every direction. You're going to get pressure not just from the top, but on every side, all around you, even below you. You're going to get pressure up against you because of the gravity. Now, how can it become a higher pressure? If you move deeper down inside here, now you have a greater weight of the molecules, or we'll say the bowling balls above you, and so it gets to be higher and higher pressure. Down here, it would be like really crazy. You have a giant weight of all these bowling balls above you. It would be like you wouldn't be able to breathe, okay? So you wouldn't want to do that. You would go up higher. Okay, so anyway, here's a lower pressure in this area. We'll just put a little arrow. I don't know if you can see that too good. But down here will be a really high pressure on you in all directions because as you go down. Well, the same thing is true on the Earth. On the Earth, I don't know if I can draw some continents or something like that, or here or there. Draw some, I don't know. I'll try to draw some continents and some over here and all this. Whatever the case is. Well, around the Earth is an atmosphere. Air. You ever thought about it? What holds the atmosphere there? It's gravity. the air is just oxygen molecules, O2, nitrogen. 80% of all of this around the Earth is nitrogen. Almost 80%. Almost 20% is oxygen. And then you have things like helium, a little bit of helium, carbon dioxide, really small amounts of water vapor. But the bulk of it is this stuff. What holds those molecules there is gravity. Gravity's pulling on them. So as you go deeper, think about a cross section. Let's just say that we made like a big cylinder or something, or a chamber here coming down. If you came down into this from outer space, there's no air, no problem, nothing going on. But as you come to the first part of it, it's very, very light amount of air around you, very low pressure. Deeper and deeper and deeper you go, a very high pressure. Because now you have, think about the air as being like a bunch of billions and billions and billions of like little bowling balls or tiny little balls. They're getting pulled against you. Same thing is true when you swim in the water. When you go deeper, you feel more pressure on you. You can really notice it on your ears. When you drive to a mountaintop or down, or you descend from a mountain down, or if you're in an airplane, you ascend or descend, you notice your ears popping and all that as well. Because what's happening is, if the air is less dense, like up here lighter, then it's one pressure, and then it's lighter pressure, I'll say at a high altitude, and at a lower altitude, I'm sorry, did I say higher? It's low pressure at a high altitude, and high pressure at a low altitude. Just think about that little diagram, the deeper you go. So anyway, that's just one thing I wanted to bring up to talk about air pressure. There's some interesting things there as well. I don't know the whole physiology behind it, but like for a person, inside their ear, we'll draw some little ears here on this guy. Okay, so inside your ear, that there's the membrane there, the tympanic membrane, right? I think I remember that. Well, anyway, what happens, the way you can hear sound? Well, that membrane is skin, and so the air pressure is constantly hitting that. I mean, it's hitting all your body. The air pressure is all around you, but it's hitting this. Well, what happens is inside your ear is like there's carbon dioxide. I know that CO2 gas is in there, and it's kind of like a balloon. There's the pressure of the carbon dioxide will always equal the pressure of the outside. It has to always be equal inside and outside for you to hear correctly, okay? And probably for more than just that, probably physiologically. So that pressure has to be equal inside and outside, all right? Inside the carbon, I didn't draw a good, you don't have giant balloons inside your ears. It's probably a very small amount of area or volume, but basically that pressure must equal the outside pressure. That's what we're trying to get at. So how do you change the pressure inside and outside is when you yawn. So I don't know if you've noticed that, but like when you say that, like, oh, who makes me want to yawn? Okay, so when you yawn, you're changing, you're equalizing the inside and outside pressure. What's interesting is you can even yawn without, you don't have to breathe to yawn. I don't know if you noticed that before, but like when you're swimming underwater, kind of in there, you're changing the air in and out, the air level. So at a high pressure, if you go down to a high level, down to a low, if you go to a very deep level where it's high pressure, you have to build up and put more carbon dioxide in your ears to match the outside for the water or air for that matter. At a very high altitude, when it's low, now you have to let some out. And okay, so the danger, you probably heard about divers. The danger is if you go down in the water too deep, if you go too fast down, or too fast ascend or descend too quickly, you can damage your ear inside there. Because imagine, suddenly, if that thing doesn't match the outside, that's quite painful, okay? So that's why they say to do it very slowly, ascend and descend. Okay, well anyway, the other thing I didn't mention it so much, but it makes sense, that like, if you have the ocean here, and you have some sand here, and you have a mountain here, or whatever, high up on the mountain, you have a very low pressure. Or in a valley, like Death Valley or whatever, deep down in a valley, if that valley wouldn't get flooded, deep down in the valley, you have a very high pressure. So high air pressure when you're deep down in the valley, because you got even more air above you. High on a mountain, you have a low pressure. Okay, so the barometer will be, as I told you, at a high altitude, back to my little picture again, you won't hold the liquid up as much. At a very high altitude, it'll go down. Less air, less collisions. And at a high, at a low altitude, it'll be a higher up. Okay, so the scientist that invented the barometer was named Evangelista Torricelli, and so it just shows you what was used was mercury. Mercury's a liquid. The reason they use mercury, I think I put it in the notes. I put the reasons in there, mainly because it's very dense. And I'll tell you this: this is not really a good barometer. Here's what you wouldn't know: if I filled up a glass tube of water completely, and I put it underneath in the ocean or whatever, and I took my thumb off while it's under the water. There's a lab we do that way, actually. There's a lab like that we do in that manner. Take a giant glass tube completely full of water, put your finger on the top so that no air can come in, no air out, no water in, no water out. Put it upside down. Well, if you could even do this, do you know how high the tube could be? It could be 32 feet high. That's maybe like a 3 or 4 story building. That is how strong. You could actually have a giant tube that's 4 stories high sitting in this small little container of water, and you'd be able to hold the water all the way up in that tube to the very top. Okay? Now, if you go higher than 32, then what will happen is you'll have, like I have here, empty space above it. Okay? Because the Earth's gravity how would you say that? The pressure will not be able to overcome the Earth's gravity. The pressure can match the gravity of the Earth for water by holding water up 32 feet. Okay, so that would not be a very good barometer. You don't want to have to stand up 31 feet high to see what the air pressure is. So with mercury, it's a lot more, makes more sense. If you have a tube of liquid mercury, what you do is you immerse it inside liquid mercury. And what it turns out is pretty much, it could be about 1 meter long. A meter stick could be used. 1 meter is 1,000 millimeters. And so it turns out mercury, which is a liquid silver color, not green, but I'm going to just use green. So if I have mercury submerged in a little bit of mercury, guess what? If you go at sea level anywhere around the Earth, it will be 760 millimeters high. And that's where we get 700 millimeters of mercury. That will be the height at sea level anywhere on the Earth. If you go to any ocean and you stand there. Now, with regular normal weather conditions, under crazy weather conditions, it can change. But anyway, it'll be 760. Okay, that's standard atmospheric pressure. Now, if you go above sea level, if you take that with you, go up higher, now it will drop down, get lower and lower pressure. If you take it down like into a valley, like Death Valley, deeper and deeper you go, it'll go up above 760. But even around here, you'll see in a lab, sometimes the pressure can be 765, 764, or 50. Yeah, it could be a little bit above 765 or 758 or whatever. It could be up or down. So, all right. Anyway, that is how the barometer works. And I think I put in the notes, let me just look at there. It was under 5'11". There was a picture of him. I always talked about how they're so mean to the poor Italian, Torricelli, how they decided to just they just chopped his name off, All the other scientists, there's a unit called a Pascal, PA, that's a scientist's name. Newton, there's a unit in physics called Newton. Pascal, there's many of them. Ohms, have you heard of that? But look at what they did. I mean, why did they do that to him? They took it off. Torricelli, I said, Italian, that name's just too long. We're just going to cut it off and make it Tor, So, oh well. So, millimeter mercury, Tor, and Tor. All right. Now, all righty. What is the next little thing on the list to go over? Now we're getting into 510. So, like I said, I might end up having multiple videos here, but this is you can do as you want. You can pause this one or however you want to watch them when you're doing these. Okay, so 510 talks about the kinetic molecular theory. Now, this section, let's see. Okay, the first part of this talks about what is work. We don't really have to go as deeply into it, but I'll just tell you that the physics definition of work is always defined as Well, how about this? Energy is always defined as the ability to do work. Now, in physics, the word work does not mean like your job work or like, labor, hard labor. Oh, I really had to work hard, lifting things and all this. No, well, actually, it's similar to lifting and all that. It's the ability to I'll just say influence the state of motion of another object. Ability is the energy, the ability to influence the state of motion of some other object. Think about that. When you eat food, you get energy, we say. Okay, energy can be measured in joules. That's the metric unit. And it can be measured in calories. That's the U.S. Imperial British, English, U.S. is calorie. Okay, so just give you a quick idea. So if I take let's say that there's someone's throwing away a refrigerator is sitting out on the ground near a dumpster, and you decide to go up and start pushing it with some friends or whatever. I don't know why you'd do that anyway, but okay, it's a heavy object. When you push that refrigerator across the ground, if you move it any bit of distance at all, you did work on it, okay? Well, guess what? Like, you could actually measure and say, all right, they pushed the refrigerator across the ground and they did 200, how about, let's make it 2,000 joules of work were done as they moved it across as the guys were pushing it and they around across the ground. They did 2,000 joules of work. Now, that's physics that we're not going to get into. But I'll just tell you this. In order to do 2,000 joules of work, you measure the distance, and you have to measure like the friction, how much force it took, how much force over what distance is basically how you do it. But if you said you did 2,000 joules of work in moving that refrigerator, guess what? It required 2,000 joules of energy. The guys that were all pushing it, or maybe some girls were out there doing it too, they had to eat some food in their bodies to give them calories, or to give them joules. We'll just say joules, use metric. We had to get calories in us, then you can do work by doing that. Okay, well anyway, I'll just put that in there. Energy is the ability to do work. Kinetic energy is energy objects have due to motion, because they're in motion. And we know that gas molecules are in motion, and they can do work. When a gas, we talked about that before, if you increase the temperature of a gas, well, now you know the volume expands. Why does it do that? Because the molecules are moving faster. They have more kinetic energy. That means that their collisions are more forceful, and they're moving faster, and they're more frequent as well. You'll see. We'll get to that in a minute. They're more forceful, so they're able to do more. They're able to do more work. Okay. Well, I don't want to bore you on this. I will tell you this is a good equation to look at, and I've shown it to you before. 1/2 mv squared. The kinetic energy of a substance or a molecule in joules would be 1/2 times the mass. If you put in the mass, it has to be in kilograms, and the velocity v has to be in meter per second. Now, this used to be on the AP, and it is in your textbook. Well, this general students might be watching this as well. This used to be, but now it no longer is. But I do like you to know that equation. And I even have some worksheets on it, but we're probably not going to deal with that. Another equation for kinetic energy, I believe this one might be in there, 3/2 RT. Now that one I'm going to talk about in a little bit, but that's pretty interesting. So it tells you can calculate the kinetic energy based on the R and T. Well, now that I threw that out at you, let me just tell you, the R value has a different unit here. Anytime you're measuring in joules, the R value you use is 8.314 joules per mole Kelvin. So, anyway, I better not get into that. I think it's going to come back to this in a moment. But anyway, let me take this part away. So, this is no longer atmospheric pressure. We're doing 510, kinetic molecular theory. Okay, so, yeah, you see, actually it's right there on the notes, 3/2 RT. Oh, nRT. I left off the RT. Well, that equation I showed you is for 1 mole. The kinetic energy of 1 mole of gas equals 3/2 RT. But then if you want to have the number of moles, you put nRT. But we're not even going to be calculating with that. But That's why. Okay, so there's an equation there. There's some problems, but we don't do them anymore. So aren't you happy about that? So that means now we're at 511. But I guess it's good to know that equation, 1/2 mv squared, because it tells you, like we did this on Graham's law, because I teach it before I did this, having a greater mass, if two objects have the same velocity, like say a little Volkswagen crashes into knocks down a stop sign or whatever. A Volkswagen knocks down a stop sign. The Volkswagen's going at like whatever, 50 miles per hour. Okay, or let's just say that an 18-wheeler truck is going 55, the same speed, let's say 55 miles per hour, and it hits a stop sign. Which one's going to do more damage to that stop sign? Obviously the giant truck, because it has a big mass. Having a larger mass, even with the same velocity, a larger mass is going to be more forceful collision. On the other hand, if you have a small mass, let's just say that an object has a very small mass, like the Volkswagen, a little baby mass, but it has a very big velocity. Well, now it could match the 18-wheeler. Okay, all right. So this really talks more about the kinetic molecular theory. Objects, molecules are kinetic, in motion. In the solid, the liquid, and the gas state, where do you think the molecules are moving the fastest? Obviously, you'd say the bigger speed would be for the gas molecules. They're moving around a lot faster right there. Yes, so usually that's a lower temperature, a middle temperature, and a higher temperature. I mentioned this in a past lesson as well. I know I did say that. So anyway, I think I also mentioned to you, didn't I also talk about absolute zero? Or if not, I'll do it right here. I believe I've said it at some point. Kelvins, 0 kelvins, okay? If you take a graph, and I've mentioned this before, I believe, but if not, here I am again with it. Let's just say you put pressure here, and down here on this axis you put temperature in degrees Celsius. Or you can make another graph that is volume right here on this axis, and down here you'll put temperature in degrees Celsius. First, I'll go with the pressure. I don't have a pressure gauge with me, but actually I have this. I can just show this to you. I was trying to fix my computer on something that just has pressurized air inside there. Well, you know that if I were to heat this up, and I could put a pressure gauge on it, it always says, do not throw into a fire, do not store at high temperatures. Why? Because it's Guy-Lussac's law. The gas molecules are going to move faster and faster, and it's going to cause a higher and higher pressure inside that chamber. So if you measured the pressure, let's start at 0 Celsius. Let me take that away for a minute. 0 Celsius, and let's just say the pressure at 0 is right here. Well, then you go higher, up to 100 degrees Celsius. Maybe we'll say right here. You go all the way up. The pressure continues to go up. As the temperature goes up, the pressure goes up. Or if you put it in colder and colder water, I better put it up here a little bit. Colder and colder water, it goes down. Well, it turns out that scientists realized, somebody, I guess Kelvin is the one who gets the credit for it, named Kelvin, that if I made this makes a line, it's linear with temperature. So if I draw a line, oh no, I'm not doing too good. Well, it's not too horrifying. It's not great, but oh well. If I draw a line and I go all the way down and I hit the temperature axis. Now, here's what should be understood. I didn't say this. This origin for where the X and the Y meet, that will be 0 Celsius, we'll say, and the pressure is also 0 right there. Up here, the pressure might be, I don't know, I'll just make up some number. I'll just put like 900 millimeters of mercury or something like that, okay? Well, anyway, so let's just say that right here at 0, at 0, well, no, I'm sorry. Down here it'd be 0, but at 0 Celsius, it's not 0 pressure. But when you go all the way down here, it looks like here you get 0 pressure. 0 pressure. 0 millimeters of mercury or 0 atmospheres. Is it even possible? What does that mean? 0 pressure would mean the gas molecules inside this thing could I get it so cold that they would stop moving around at all completely? Now you'd be thinking, well, of course it's going to turn into a liquid and it's going to turn into a solid along the way. It gets colder. Well, we're going to kind of ignore that part. But anyway, it seems to point to the fact that there is a temperature that is so low that the molecules stop moving. That's called absolute zero. And it turns out on a graph, we can do this. I have a device. We can actually do this at school on a lab, and it's not a hard lab. You can even do it you can do it another way too with volume. But that temperature ends up being negative 273.15 Celsius. That temperature. So that tells us there appears to be a lowest possible temperature, like a temperature speed limit or whatever, or sometimes there'll be you'll see on the freeway it'll say speed limit 75, minimum speed 50 or whatever, 45. Don't go slower. Well, there's a minimum. That is the lowest. Well, you can't go under that or you get a ticket for going too slow. Okay, I think I've seen that more like in areas like maybe where they have a lot of trucks going through as well. And they're shipping materials and all that. So shipping, but through trucks, they don't want to have bad traffic and stuff. Well, anyway, there's a temperature so low, it appears that that's the lowest possible temperature is negative 273.15 Celsius. You couldn't get any colder than that because you can't go any colder. Temperature can't go any lower than no motion at all. Remember, temperature all along the way is measuring how fast the molecules are moving. In fact, there's an equation, and it's on the next page. And I'm going to go on and show it to you right now, and we'll see it in a minute. We're not going to have to use it, okay? But it's sometimes written as U. I like to use V or VRMS. They're both used. It's a square root of 3kT over M, or it's a square root of 3 capital RT over capital M. I'll tell you what these things are. I think it's good just to know what they stand for. This tells you the speed of molecules, the speed, the velocity, the root mean speed, the average speed of molecules moving around. Let's look at the bottom one. Don't worry about, well, either one. I'll put V for both of them because I think it makes more sense to say the velocity. The velocity, how fast molecules are moving, you can calculate it as long as you know the temperature of a gas and you know R. And M is the molar mass of a gas. If I know the temperature of a gas, and I know what R is, and it'll be the R that is, it'll be the 8.314 R value, okay, for energy. But anyway, or I can use what's called Boltzmann's constant K. This number right here, 1.38, 10 to the negative 23. And put in the temperature again in Kelvin, and put in the mass of one molecule of a gas in kilograms. I'm telling you all this, we're not going to do anything with that, okay? But all of this neat is, I like this one. If I know the temperature of a gas is 25 Celsius, for example, I'll change it to Kelvin. I'll plug in what is the molar mass of that gas. Maybe if it's oxygen, it's O2, 32. I put in the mass of the gas, the temperature, and I can tell you how fast the molecules are moving on the average in meter per second. Then I could turn that into mile per hour if I wanted to. So, that's just getting a little bit of nerdy math there. I'm showing you that I used to require it. It used to be part of our lessons and in the AP, but they stopped. They took it off the AP exams. All right, but anyway, so here we go. But they still want you to be able to explain a lot of this stuff. So anyway, because of the graph that I showed you here, because negative 273, we know that they decided, we're going to shift the temperature scale over. We're going to keep the Celsius thermometer, but we're going to shift it 273.15 degrees over, and that will call that Kelvin. So if water boils at 100 degrees Celsius, then we say it would boil at 373.15 degrees, or not degrees, 373.15 Kelvin is where water would boil. Water freezes at 0 degrees Celsius, so that means it freezes at 273.15 standard temperature. Okay, so we see that. I'll just tell you quickly, I don't want to go into the details. This is just something that you could see in AP students. But you can also have volume up here, and get the same exact graph. And I don't have a way to show you that without a little device. But actually, you would take what you would do is you would take a cylinder with a movable piston. Like, you can do it with a syringe, and we could actually use this in class. And you have all these calibrations on the side, and you would read, okay, what is the volume of this gas right now? And you put it in cold water, and you see, and you have it sealed off, and you'll see it'll in cold water it'll go down. The gas inside here will move slower, so it'll go down, the volume will go down. You put it in hot water, it'll go up. It's really cool. And all along the way, if you write down, okay, at 10 degrees Celsius, it's this volume. 20 degrees Celsius, this volume. 30, this volume. And you go on and on and on. If you graph it, you will get the same thing. You only have to graph a few points over here, and then when you draw a straight line with a ruler, it will intersect at where absolute zero is, 273.15. Really cool. I have a little activity on that. I usually do that lab. One of these, I do them in my general class because it's not really required on AP, but you should know that. Okay, so what is the kinetic molecular theory? We're getting into that section, and I don't know if I'm going to let that be part of the next video lesson. I think I will. Let's see, because then I got to talk about that and real gas equation. Oh yeah, I got to talk about that worksheet as well that I have there. Yeah, I think I'm going to have to wait on that one. So I'll get that lesson out for you. And yeah, I'll do the next part. I know I would love to keep going, but it's long already. So I think in one more video I can finish it all up. But it'll take a little bit. It's all related to kinetic molecular theory, so it's kind of good to stop right here. So, all right. So I'll see you, and there'll be a part 2 coming up.